Hello folks, fellow YouTubers and friends. My name's Raymond Head. My nickname is Boomer. I own Boomer Drywall in Louisville, Texas. A lot of you people out there know me. Some of you don't. I do a lot of science experiments and stuff like that and put on YouTube, and most of what I have done are just copies of what other people have done, trying to see if I could improve it in such a manner or in some way, make it easier to build or more efficient or whatever. But anyway, the last series of videos that I put on were about converting a ceiling fan to a PMA, permanent magnet alternator. I knew it was almost fruitless in the fact that the ceiling fan, the wiring in it was so small and blah blah blah, that it's real easy to do. It's just that it doesn't put out the actual current. Now, current being usable power. I mean, you can get amperage and you can get voltage, but without the two together and some way to control it, it's almost useless. I mean, 100 amps at 2 volts. I mean, what have you got? You can't use it. There's nothing there. Or 1,000 volts at 2 milliamps. I mean, duh. Okay, anyway, I just did it just to see if I could do it easier and faster than most people were doing theirs, and I did. Anyway, I've got one more video to go on that. I've got 7 videos in a string, and I've got one more video to go on it. But I made an announcement in one of the videos on that I'm getting really down to the wire of wanting to get started on a pet project of mine I've had now for, I say, 5 or 6 years, but the project actually started when I was just a kid. I mean, watching my father's percolate his coffee in the old style percolator that you put on top of the stove with the electric stove or a gas burner, and it causes the water to boil and pumps water up and splashes it over the coffee and blah blah blah. And I used to love to watch the little glass ball, the hollow glass ball on the top, jiggle up and down and all around. And as I got older in life and learned that, if you pass a magnet across copper coils, you make electricity and all, I was thinking to myself, wow, that would be neat. If you just glued a magnet to that and then put a little copper coil over it, you could make electricity and coffee at the same time. Of course, you'd lose a lot of heat. It wouldn't be efficient. But then I got to thinking about it. Heat affects the magnetic flux in a magnet. It can actually, if you heat it up enough, which I've done an experiment, didn't put it on YouTube. If you heat a magnet enough, you can take all the magnetism right out of it, including the newer neodymium magnets. In fact, that was the experiment that a friend of mine in Scott, when he was here visiting from Venezuela, named Beto Carrera, he likes to, well, his English isn't all that great, so to experiment, I mean, he calls it wrecking. He wants to wreck something. Okay, great guy, great guy. Anyway, we took a neodymium magnet, 1/4 inch diameter, 1/2 inch long, and we wrecked it. I took my paint heat gun, electric heat gun, and we heated the magnet until it had no magnetism in it at all. I mean, it had none, zero, zilch. We cooled it. Still, same thing. I mean, after a couple of hours, there was no magnetism. It wouldn't even come back. So then we took some larger magnets, like I took some N50s, 1/2 inch diameter, 1/2 inch long, very strong magnet. We reheated the 1/4 inch by 1/2 inch long neodymium magnet, very hot. I mean, if you just touched it, it would have blistered your hand. But anyway, we reheated it and stuck it between the two magnets until it cooled. And lo and behold, it not only came back, but it came back with more power than before, because the magnets that we put on it were stronger than it was to start with. So anyway, you can take magnetism out of a neodymium magnet and put them back in. By the way, for all you people in countries where you can't ship neodymium magnets into your country for some reason or another, which Beto Carrera can't legally. However, you can buy neodymium magnets without magnetism. They're non-magnetic, but all the properties are there. Then all you have to do, those are legal because they're not magnetic. You bring them into your country, and then you can just simply heat them up, put them between two strong magnets, and go ahead and remagnetize the daggone things. Simple. I mean, you know, I just thought I'd bring that up. Anyway, my pet project is what I like to call a cold steam turbine. Okay? If you ask somebody what is the boiling temperature of water, 9 out of 10 that know will tell you 212 degrees Fahrenheit. That's it. Well, if they say that, they're wrong. I'm sorry. If you thought 212 degrees Fahrenheit, you're wrong. An incomplete answer to any question is the wrong answer. An answer cannot be correct unless it is complete. Now, the correct answer, what is the boiling point of water? That is determined by the pressure on the water, and which scientists have to have something to go by, so that what it is the boiling point of water is 212 degrees at sea level. Sea level is roughly 15.7 or 8 pounds per square inch. Convert it to millibars, it's 1,000 millibars. That millibars is a measurement of pressure. Now, as you increase the pressure in a steam turbine, you increase the temperature required to boil the water. However, when you boil water at sea level in an open container at 212 degrees, no matter how much heat you apply to the bottom of your pot, the water supposedly, theoretically, gets no hotter. It simply takes the excess heat, which is not temperature, it takes the excess heat and turns this water into steam. When a molecule of water at sea level reaches 212 degrees, it's still a molecule of water. Now, if you take 1 pound of water at 212 degrees and you add 810 to 970 BTUs, depending on the conditions, the cleanliness of the water, the barometric pressure at the time, blah, blah, blah. There's different factors involved, but we're going to say roughly 860, 70 BTUs per pound of water will turn that entire pound of water into steam at 212 degrees at sea level. There we go. Let me think for a second. Other liquids are the same way. Kerosene, gasoline, lacquer thinner, paint thinner, liquid propane, LPG, liquid propane gas. Liquid propane. Alright, if you took a propane tank and you hold it and say it's half full and you slosh it, well, you can tell there's liquid in it. Propane condenses into a liquid at 42 to 44 degrees below zero. Therefore, if you opened up the valve on a propane tank at 44 to 45 degrees, it would not gas out. It would be strictly liquid. You could turn the tank upside down and pour liquid propane right out of the tank. There's a video, a volunteer fireman did a video. He lived up north. He did a video on just that, showing how to do it and so forth. He lived up way the heck up north and did it one winter when the temperature was like 45, 46 degrees outside. And you get much colder than that, you definitely don't want to open the tank because there's going to be a slight vacuum in the tank. And when you open it, it's going to suck in air, which now all of a sudden you're going to have oxygen in your tank with your propane. So when it heats back up and builds a pressure, it could self-ignite. Propane under a certain amount of pressure with oxygen will self-ignite. So it's dangerous. Don't even try it. I'm telling you, don't try it. Okay, alright, here's the thing. When a liquid reaches a certain temperature, say its boiling point, then the excess heat needed to convert that liquid to a gas is called latent heat. L-A-T-E-N-T. Latent heat. Now, propane has a latent heat. When it's liquid, so you add so many BTUs to it, it turns to a gas at that temperature. Water, at sea level, 212 degrees, you add 850 or 60 BTUs per pound of water, it turns to a steam at 212 degrees. Now, what I'm thinking is it's a heat engine, like a steam locomotive years ago. All right, any heat engine will, it works on putting heat into it. The more heat you get into it, the faster you get into it, the better it works. Correct? No. Absolutely no. Incomplete answer. Incomplete is the wrong answer. A heat engine will work very fine if you just throw gobs of heat into it. Just throw the heat to it. But in order for the heat engine to work, you must get the heat out of it as fast, or the ability to get it out faster than you can put it in. Then the heat engine works. That's why the old time locomotive trains out in the Midwest years ago worked so well. They put a lot of heat into it, make a lot of steam, a lot of pressure, but they expel the steam into the open air so they could get the steam out, the heat. They could get it out of the engine just as fast as they put it in. Therefore, they work great. Now, here's the deal. Modern day steam turbines for making electricity that use gas, oil, coal, whatever, they recycle the steam. All right, so the steam comes out, goes into a big cooling system, condenses the steam back into water, and therefore you've got water at almost, boiling point. So then they run it back through the boiler and blah 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 blah. That's great. That's really great. It saves a lot of energy, a heck of a lot of energy. The thing is, what I'm going to do is going to work on the same identical principle, but I'm not going to make it as powerful, but I'm going to make it where you can just run it off of sunlight. And we're going to build a steam powered turbine, but we're not going to use the steam to turn the turbine. We're going to use the steam to push water, and the water will turn the turbine. So I guess you'd call it steam over hydraulics turbine. Okay? After this video, I'm going to try to build and I intend to build it crude, example or proof of concept device to make a video of it and show that it will work. I am 99.99999% positive that it will work. I mean, there's no doubt in my mind. Not the only doubt I have is listening to other people. Anyway, I'm going to try to use water unless somebody can come up with a better solution, a better liquid than water. Now, let's study the properties of water. Water without air in it, no air, just pure water, and I'm talking pure water. We're going to have to distill it and vacuumize it and pull the air out of it, everything. Anyway, let me put my glasses back on. The properties of water: if water is at sea level, 1,000 millibars, it boils at 212 degrees and turns into steam if you apply enough heat, which is 810 to 970, so roughly 860, 870 degrees, not degrees, but BTUs per pound of water. Now, a cubic inch of water, I've got the calculations right here. Okay, a cubic inch of water weighs 0.5774 ounces. Okay, so that means that you need 3.5 to 4.12 BTUs per cubic inch. Now, what I want you to understand is that when water turns to steam, it expands. 1,600 times its size. So if you take 1,600 and you find the cube root of it, you're looking at 40. So 40 cubic inches, I'm sorry, 1 cubic inch of water turns into 1,600 cubic inches of steam. Now you take 1 cubic inch and turn it into steam, it fills a box 40 inches by 40 inches by 40 inches. That's a lot of power if it were under pressure. But you need, in order to get it under pressure, you have to put a lid on it and you have to let the pressure build. But as the pressure builds, so does the requirement of the temperature of the water. Now it takes 1 BTU of heat to raise 1 pound of water at 1 degree Fahrenheit. So if you're boiling the water at 212 degrees, you've got a lot of steam that's not doing anything. Okay, so you put pressure on it, and let's say you raise the pressure to a certain PSI, sufficient to use the steam power to turn a turbine, then you've got to put that much more heat into the water to get it up to its boiling point so that you make steam at that pressure. Okay? Alright, that sounds good. Now all of a sudden you've got steam under pressure in a container. So you have the possibility of a leak, pinhole leak. Now on military ships that use steam powered engines, I've had several friends of mine in the Navy. In fact, my pop was in the Navy. My stepfather, I call him Pop. And everybody told me in a steam engine, in the engine room of a ship, if anybody whistles, they get their jaw broke. Because steam coming through a pinhole has a real shrill whistle. So you never whistle. You listen for whistles. If you hear a whistle, you've got a leak. You never run your hand across the pipe to find the leak. It will cut your fingers right off. You're talking 600-800 pounds of 300-400 degree steam. I mean, just cut it right off. You take a broom handle and you run it up and down the pipe. When the broom handle cuts in half, you know that's where the leak is. Anyway, that's neither here nor there. The thing is, when a molecule of water at boiling point absorbs the amount of heat necessary for it to convert from water to steam, it depending on how fast you put the heat in, you put it in very slow, like sunlight on a mud puddle. It puts it in very, very slow, so the water on the surface says, "Oh, I'm getting hot, I'm getting hot," and it expands and floats off into the air. But in a boiler system, you're throwing a lot of heat, and all of a sudden this one molecule gets so hot, it says, "Whoa, whoa!" and it's an explosion, a literal explosion. But now if you put enough heat, you get several billion of molecules exploding simultaneously. You get an unbelievable explosion. And that explosion in the water pushes all the other water that has not absorbed that much heat, pushes it in all directions. That's what we're talking about here, folks. We're not going to use steam pressure as steam to push a turbine. We're going to use the actual conversion of the molecules of water into steam to push the excess water and use that power to turn the turbine. I'm hoping a lot of people understand what I'm talking about here. But this video is just nothing really more than an introduction to a series of videos I'm going to make on building this thing. And like I said, the first video that I do with an actual build is going to be extremely crude, just to prove it works. Now we've already got the finished product, I mean, pretty well designed, and it's really, really fantastic. So I want to do 1 or 2 crude experiments, maybe 3, very crude, to show that it will work, and then we're going to get down and build. I mean, we're going to use some finesse in this. We're going to build a turbine that's out of this world. It's going to be very small. It's going to be 4 to 6 inches in diameter, maybe 4 to 6 inches long, and how much power it's going to put out, I don't know. But if you watch my videos, you'll find out right along with me, folks. All right. Hopefully I've said enough. I don't want to tie up too many people's time. I just want to make this as an introduction to the cold steam turbine, and that's what I'm going to label this video. Introduction to the cold steam turbine. Nice seeing you again, folks. Y'all be good.